Right, so I was asked to give a talk about recent highlights, but I've decided to focus mostly on the results from the dark energy spectroscopic instrument. There were a series of papers on April that I think are quite cool, so I'm going to focus on that. Those are galaxy maps from DESI. So yeah, so my name is Andreu from Ribera. I'm in the university, so I'm in Barcelona, the High Energy Physics Institute. But the presentation that I'm going to be giving is showing results from the whole dark energy spectroscopic instrument, DESI. There's almost 1,000 participants in 72 different institutions. Funding agencies is a compulsory slide. And also STFC is one of the funding agencies that gave a significant amount of money. So this is the highlight that I'm going to be presenting in one slide. So using data from the first year of the dark energy spectroscopic instrument, we have measured distances to 7 different redshifts. So you can see, oh, there you go, sorry. So going from redshift 0.2 or something like this to redshift 2.5 or so. So we have measured distances to 7 different redshifts using different types of galaxies. So we have maps of galaxies. We look at the correlations, and we see this sharp feature in the correlations of galaxies. And we use that to measure distances to these redshifts. And I'm going to be showing a lot more detail on those later on. So first, I will start with an introduction to BAO. What is this technique? Then I'll talk about the instrument of DESI. And finally, I'll go on the cosmological results from this first year. So in 2004, maybe something like 20 years ago, there was the Dark Energy Task Force. It was a committee set by US funding agencies to figure out what is the best way to make sense of dark energy. And there were 4 probes that were proposed. 2 of them looked at growth of structure, and those are weak lensing and clusters. 2 of them looked at the expansion of the universe and how it changed with time caused by dark energy. So one of them was supernovae. That's the original one that was used to make the final detection after the hints that we had already for 10 years or so. But the one that I'm going to be focusing on is BAO, and that's something that we call sometimes a standard ruler. And what that means is that if you know the physical size of an object and you measure the angular size at different redshifts just with basic trigonometry, you can infer how far those objects are. Unfortunately, the universe does not give us objects of a fixed size. You cannot say all the galaxies have 1 megaparsec and we're going to look at them at very different redshifts. But there's this idea of baryonic acoustic oscillations that we can use instead. So this is an animation from Daniel Eisenstein that shows in the early universe, if you have an overdensity of matter and radiation, there will be a competition between pressure and gravity in the plasma, in the radiation baryon plasma in the early universe. And this will cause an acoustic wave. So this overdensity will cause an acoustic wave that will expand. And it will expand all the way until the redshift of 1,000, roughly, where there's recombination. So that's the same time where the CMB photons are released. And at that point, the acoustic waves stopped. And the distance that they traveled is what we use as a standard ruler. So using fairly simple atomic physics, we can compute what would be the distance traveled by those waves as a function of things like the density of photons, the density of baryons, and so on. And we know that this is a distance of roughly 150 megaparsecs. Sorry. This is not, should I point here instead or no? Okay, this is good, right. So 150 megaparsecs or so. And this is the ruler that so there's this particular imprint that we also saw in the talk by George, these oscillations in the CMB temperature power spectrum. Those are the same acoustic phenomena, and they leave an imprint also in the distribution of matter. So this is an artistic view of this imprint on the distribution of galaxies. But what we do is we have these catalogs of millions of galaxies, and we look at 2 different things. One is we look at the correlation of these galaxies as a function of angular separation. And we detect, sorry, that's going to take me a while to get used to this. So we detect a particular angle where there's an excess of correlation, and using trigonometry, because we know that the sound horizon RD, we know its value, then we can infer the distance to those objects. And then what is also quite cool, that happened like a few years after the first detection, is that we can also detect an excess correlation, not as an angular separation, but as a line of sight separation. So we see that galaxy pairs that are separated by a particular redshift difference are more common than redshift difference a bit larger or smaller than that. So by looking at the line of sight correlations, we can also detect this excess correlation at a given delta z, and from that we get a direct measurement of the expansion rate of the universe at that time. So then we do this at different redshifts because we have galaxies at very different redshifts in DESI. So we have at the end 7 different measurements of the BAO distance along the line of sight and transverse, and by combining that we can put constraints on dark energy and other cosmological parameters. Right. So let's move to DESI. So I used to talk and show some plots for a couple of minutes explaining the instrument, but DESI made this really nice video.
Light first reflects off of the telescope's 15-ton primary mirror, then onto its 6 large lenses that ensure DESI maintains a wide, highly focused view of the sky, covering an area about 38 times larger than the full moon. These lenses are housed in a device that can be adjusted within millionths of a meter to preserve the alignment of those lenses. After passing through the set of lenses, the galaxy's light reaches fiber optic cables in DESI's focal plane at the top end of the telescope. 5,000 robotic positioners, each carrying a single optical fiber, are programmed to move to pre-selected sequences of galaxy targets. This automated dance of robots allows DESI to target sequences of thousands of galaxies at a time. The optical fibers, which serve as DESI's eyes, send the galaxy's light down the length of the telescope to 10 spectrographs.
Right. So let me show you one extra plot about image from the DESI corrector. So this corrector with all these 6 lenses were aligned at UCL. So this is a picture taken at the workshop. And I think it was Hiranya who took that picture, right? Yeah, I remember. So, and then I moved to Barcelona, and Barcelona was also responsible for a smaller part of the instrument. They built the guiding and focusing alignment cameras. So there are 10 little cameras that are in the focal plane that help DESI figure out where it's pointing at, because, you know, since we have only fibers, it's hard to guess, to do like the guiding and the focusing. Anyway, so the instrument started in 2021. The survey started in 2021, and the original plan was to do a 5-year survey. Might be extended, but the original plan was 5-year survey. We're already more than halfway through. We're actually 70% already complete. And during those 5 years, the idea is to use this instrument to look at different type of galaxies and obtain 40 million redshifts. So that's a significant larger number than what BOSS and eBOSS, the predecessors, found. And what we do is that when the moon is up, the sky is a little bit bright, so it's very difficult to look for very faint objects. And in that case, we look at these bright galaxies. So we'll observe 13 million bright galaxies that will let us go to redshift 0.4 or so. Then we use luminous red galaxies to go all the way to redshift 1. We'll have 8 million of those. Then emission line galaxies to go to redshift 1.6. And finally, to go to earlier in time to very high redshift, we use quasars. And we use quasars in 2 different ways. We use quasars as tracers, just like any other galaxy. But we also use quasars as background sources to look at the Lyman alpha forest. So I'll have one slide on the Lyman alpha forest, but then Vitir after me will talk a lot about the Lyman alpha forest. So here you have results from the DESI data release 1. So this is the first year of DESI observations. It included the data taken from May 2021 to June 2022. And you can see here the number density of the different galaxy tracers. So bright galaxy survey, bright galaxies, luminous red galaxies, ELGs, and quasars. And already only with the first year of data, it's 3 times more than all the BOSS, eBOSS, and of course, 2DF and previous surveys all combined with just 1 year of DESI data. So I think that's quite impressive. And then if you go to higher redshift, to redshifts above redshift 2, we also have these quasars that I was mentioning that we use for the Lyman alpha forest. So we have 420,000 lines of sight that we observe with this Lyman alpha forest technique that I will describe briefly. And that's also a factor of 2 more than previous surveys combined, only with the first year of DESI data. In terms of footprint, the observations that we have are split. We basically cover 1/3 of the whole sky, and we cover it split in 2 patches. There's the North Galactic Cap and the South Galactic Cap. The gray area is the final footprint that DESI will observe. And what you see in blue, every blue circle is one pointing of DESI. So every 15 minutes or so, DESI points at a different part of the sky and takes an observation with 5,000 fibers and collects 5,000 galaxy redshifts, 4,000, because some of them are for like sky subtractions, calibration, stars, blah, blah, blah. But when you see colors that are blue, light blue, green, yellow, orange, red, this is that we have more than one pass in that area. So we will observe all the footprint with 7 passes to improve the completeness of some of these galaxy catalogs, but also to increase the signal to noise on the quasars, because we love quasars, so we're going to have more signal to noise on those. So you can see that the year 1 footprint is a bit patchy, especially in the south, it's quite shallow. But the equatorial line, the equatorial band here was was prioritized also because of their overlap with lensing surveys. Okay, I think I'll just give up on trying.
Point to here, everything that you do here.
So here you can see? Okay, perfect. Okay. So, so I'll use the equatorial. Anyway, yeah, good. So, so the first year of observations is a little bit patchy, but it's already a very large data set that we have used for the first BEO measurements, the first cosmological results. And that was in April 2024, we published these papers, we posted them on the archive. On the same day, it was the end of the year 3 observations. So I already have this plot that includes the first 3 years of DESI data. That's almost 70% of the survey. And you can see now that the complete area is much larger than that. You can also see here in black, if you see those circles here, those are all the pointings that we did on the last night of observations of year 3. And those are 100,000 redshifts in one night. So to put some context, this is half of the complete 2DF survey that George mentioned before in just one night. And it's twice the number of galaxies that Eisenstein and collaborators used for the first detection, for the first measurement of the standard ruler of BAO. So, right, so just to show the results that we published in April, so the DESI DR1 results will have 7 different papers, but only 3 of them appeared on the archive on April. The other ones will appear relatively soon, and those are the BAO measurements that I mentioned. Keep an eye on the archive in the fall. Hopefully in October, November, you should see the results from the redshift space distortions of galaxies. That's a different project, but using the same galaxies of DESI. And the results that I showed in the beginning of the 7 measurements of BAO, this is like more like the science equivalent of the plot that I showed. And on the left, you can see what we call the isotropic BAO measurements. So this is combining the line of sight and the transverse to a single isotropic scaling of BAO. And we have these 7 different measurements that you can see in different colors using the different tracers. And on the right, this is what we call the anisotropic BAO. It's the ratio of line of sight versus transverse measurement, also known as Alko-Paczynski parameter. And the main takeaway message of this plot is that the dark line, the black solid line, it's our best fit lambda CDM model, and it describes the measurement very well. So, it's a model that only has 2 parameters. We have 12 data points, so 10 degrees of freedom, chi-square of 12, right? So the key takeaway message from these first results is that the DESI BAO results are very consistent with a flat lambda CDM universe. It is also true here that there are some mild differences between the DESI, so this dashed black with the gray contour, this is the favorite model from Planck. So it's true that there's like between 1 and 2 sigma tensions, depending how exactly you compute it, between the model favored by Planck and the model favored by DESI, but it's consistent with the statistical fluctuations. And those points here that I was showing, those are the Lyman alpha forest measurements that I mentioned. And I wanted to show one slide also because Andrew is in the audience, and I think I've shown this in front of him like 10 times, so I thought I should just do it 11 times. So you probably know what the Lyman alpha forest is, but it's the phenomenon that explains that when you look at the spectrum of a quasar, you see a very large number of absorption features, and we know now that those absorption features are caused by intervening neutral hydrogen along the way. So when the light travels from the quasar towards us, it's every time it encounters some neutral hydrogen, it will cause some amount of absorption. And then, of course, the light is redshifted, so the next neutral hydrogen atom will absorb in a different wavelength. So I think it's really cool that this phenomenon allows us to make maps at redshift 2.5 that are accurate enough that we can measure BAO at 1% precision. And I think it was not granted when we started this business that we were going to be able to measure these things so accurately. So, okay, so I'm going to show very few cosmological constraints results because I only have 1 minute left, but also because Lice Verde is talking afterwards, after the coffee break. But if you want to feed lambda CDM with DESI BAO results, well, with BAO results in general, there are just 2 free parameters. The overall scale of the BAO in units of velocity, so that's h naught times RD, and then the density parameter omega m. The good thing is that different redshifts give you different information. So these are the 7 different redshifts tracers that I mentioned. And how do they tell you information about these 2 parameters? And you can see that they all nicely overlap, and that they overlap in the black contours that give you a 5% measurement of omega matter and a 1% measurement of this overall scale of the BAO. So now I'm going to take the black contours that are the DESI DR1 BAO measurements and compare them to other measurements. This is the last cosmological plot. And you can see here that blue is the DESI results, orange is the SDSS results, and pink is what you get from Planck plus CMB lensing from ACT. So they're very consistent. It's true that the BAO measurements are pulling CMB towards slightly lower omega m, closer to 0.3 instead of 0.32 or so. But they're very consistent, and I think this was a very good confirmation of the model. And just to finalize with a summary slide, so DESI is working really well. We are actually even ahead of schedule. And we have already provided, a catalog that is 3 times larger than all the previous galaxy surveys together. And the results are consistent with flat lambda CDM and with Planck, at least when treated alone. As you will hear later with the talk by Licia, once you add supernovae and other data set, things become more interesting. And the papers are public, so please take a look at them. And yesterday I decided to add a little bit more of like a future view, not so much about what we have now. So what's to come? Of course, the next results will be the DESI galaxy clustering results on redshift space distortions. But I also think it's important to realize it's something that I wasn't sure this was going to be the case, but there's a lot of momentum, especially both in the US and the European community, to design the new generation of spectroscopic surveys. So in the US, we are talking already about the extension of DESI. There's also DESI 2. 2 months ago, there was a meeting about SPEC-S5. In Europe, there's also WST, but there's also FORMOST that will come way before that. So we're going to have spectroscopic galaxy surveys for many, many, many years to come. And one of the things that I think has been changing is that if you look at the names of the current surveys, they all have names related to dark energy, right? There's DES, there's DESI, there's DESC. By the way, really confusing, especially in a high energy physics institute. Every time I say DESI, they think of Hamburg. It's like so the good thing is that I think all the next generation of experiments are shifting the focus from dark energy to inflation and other probes. Also, a lot of interesting forecast on dark matter, looking at nearby galaxies and our own Milky Way. But yeah, we'll have spectroscopic surveys for many years to come, and that's it. Thanks.